Hello, people. So first block, you guys saw this morning. Second block, or sorry, fourth block, you did not, and you will not, because I'm not here this afternoon, or I wasn't here this afternoon, as you saw. Um, but anyway, we have this flying pig. One pig's fly. It's today. Um, that, that tied to a string flies in a circle. Right? It flies in a circle at a nice constant speed. Now, let me back up a little bit. If you remember, we started our gravitation investigation with the question about how fast does the space shuttle or anything have to move in order to remain in orbit. Well, so our approach to that was to look at gravitation as a force, to look at gravitational field, and we have to now look at the idea that orbits, at least ones that we're able to handle in this class, are circular, and are a great example of what we call uniform circular motion. Right? The uniform part deals with this, that we say things move in circles at constant speeds. All right, so we're going to talk now about the circular motion part. Learn, get a whole bunch of sort of tools for solving circular motion or investigating circular motion examples, and then we'll go back into that gravitation and circular motion thing together and talk about orbital stuff. All right, so we got this pig flapping away, flying in a circle. All right, real important question is, does the pig accelerate? Well, the answer is absolutely. All right, yes. And how do you know? Well, what makes it accelerate? I don't know what the answer. Well, I guess how do we know, right? The big deal. How do we know that the pig accelerates? There's a change in direction, right? Even though speed stays the same, if direction changes, velocity changes, right? Well, what makes the pig accelerate? TLP, this little piggy. What makes this little piggy accelerate? Well, what makes anything accelerate? The fact that there's an unbalanced force. All right, what is the unbalanced force here? Well, if we look at the pig, we have a force like this, tension. We have a force like this, mg. This tension force has components, right, Ty, and then this one that points in, for now I'll call it Tx. And so what makes the little piggy accelerate? Well, the unbalanced Tx, right? There's an unbalanced force. There's a net force acting on the pig, right? These two forces will be equal and opposite. This is almost like that test question you had about the fuzzy dice. Well, this is different. So yeah, there's definitely an unbalanced force, and that's what makes anything accelerate. All right, now, a lot of people will get to this idea that things that move in circles are being pushed outward, right? Well, there's tension on the string, so that must mean that something's pushing this thing outward. All right, well, that's a big misconception alert. Nothing, right? I mean, look at our free body diagram. There is no outward force. Nothing's pushing this thing outward, all right? What we'll get, well, maybe I'm going to think if the future slides get to that idea. But for now, we'll leave it at that. There is no force that pushes this thing outward. All right? There's a reason why it almost feels like it's being pushed outward. And some of you might have some inclination or some intuition as to why that is. But we'll get more concretely into that as we go forward. Yeah, let's look at this top view. Right? Let's say that the pig is here. All right, so the net force at any instant. Well, one thing we can't see from our top view here is the vertical, the Ty and the mg. But what we do have is a force that looks like this, right? That was our Tx. Well, if we looked at an instant over here, well, that force Tx points that way. If we look at an instant over here, well, that force Tx points that way. So ideally, we can see that at any instant, the direction of the net force is toward the center. All right, for anything that moves in a circle, The net force is always toward the center. And therefore, what direction does this thing accelerate? Again, toward the center. And there's a word we use that means toward the center. All right, that word is centripetal. Centripetal means toward the center, right? So what we say is there is a centripetal force that provides a centripetal acceleration. And the centripetal direction, the direction toward the center, becomes our new direction. All right, we're not just going to say X. We're not just going to say, well, really, yeah, X or Y. If we mean towards the center, we're going to call it centripetal. So we're going to have a new whole net force statement, or at least, you know, a new direction to talk about that we'll have to do, well, a centripetal net force. All right, positive means in, negative means out, into the center, out from the center. Okay? Okay. Now, yeah, this is real. This is big. You know, centripetal force isn't. You know, we're not going to add W, A, N, T, F, and now C. All right. So centripetal forces aren't their own forces. They can be provided by one of our 5 forces. Right. I'm going to put in parentheses gravitational force. All right, what I'd like you to do is pause for a few minutes and think about, you know, when's there a case, in what sort of situation might a gravitational force provide a centripetal force, right? When does a gravitational force point towards the center of an object's circular path? Or when does a push point toward the center of a circular path? Or when does a normal force, and so on and so on. All right, see if you can come up with an equation, or sorry, not equation, but a situation in which each of these 5 forces could provide a centripetal force. I will tell you, applied is the hardest one, because when do you really just push on something such that it keeps going towards the center? It doesn't happen all that often. So pause, jot down some notes, maybe in pencil, and then restart. Come on, pause. Okay, so weight forces. Well, for objects in orbit, right, gravitational force between, well, you know, if we have the Earth, and here's a satellite, right, satellite moves in this circular path, gravitational force acts inward, right, therefore gravitational force is a centripetal force. Right, that's really the only one where an object's weight provides a centripetal force. Applied force, I'm going to skip that one because there's really not a great example. I'll show you one. It's a little bit, what's the word I'm looking for? It's a little bit out there. I don't know. Normal force, okay? When could the fact that an object's in contact with the surface make it move in a circular path? Well, how about this? Clothing in a spin cycle. Spin cycle is a washing machine cycle. They're trying to get all the excess water out of there. And so, you know, the drum, the washing machine drum looks like this. Here's a pair of socks. And no matter where the pair of socks are, the normal force points in towards the center. All right, as this thing rolls or spins around. Lots of other examples here. How about this? A roller coaster loop. Right, so we have a loop that looks like this. You know, the track is a surface. And if the car is here on the track, well, the normal force points in towards the center. Okay? Tension. How about this? How about a swing set? All right, so it doesn't have to be a fully, you know, here's a side view of a swing set, right? You got a little brace there, and this, you know, here's person on the swing, legs and feet, and hands and head, bigger legs, thigh there. Yeah, so swinging back and forth like this, it's not, you're not going to go in a full circle, but that is part of a circular path, right? So someone swinging on a swing set, the tension force provided by the chain is right there. I hear some of you saying, well, isn't that a normal force? Sure. Normal force acts on the person, tension acts on the seat, right? So you kind of have a couple of options here, right? You should Google hammer throw. It's not actually throwing hammers. That's an Olympic event, I think. Maybe it's part of the decathlon or something, or pentathlon, one of those. But the hammer throw is a ball tied to a rope that you swing around like a maniac and then throw. You should totally Google that and watch it. These guys are psycho. Friction. So here, the kind of question is, what I like to think about this, or the way I like to think about it is I say, all right, is there a case where if there was not friction, an object would not be able to move in a circular path, right? And if you think about it that way, you might be able to get to the idea of car on curve. All right, so as a car, this is kind of like a end-on view. Here's a car, the back of the car, tires, top. Oh boy. So the frictional force here, yeah, actually acts in towards the middle. Hard to see. You can't see it like you can see this tension force, like you can really imagine this. But if there was not friction, right, if you hit a icy patch or an oil slick or something like that, that would get rid of friction between tires and road. That says curve, by the way. That would get rid of curve, friction between tires and road, and suddenly this car would not be able to move in a circle anymore. All right, so that's the big one for friction providing centripetal force, car on a curve. Okay, applied force. This is another good inertia ball example. So remind me, and we'll at least have a short stint of inertia ball play to demonstrate that. But the least common of them all. All right. Some terminology we need to be comfortable with for circular motion stuff. There's two big ideas. There's this one called period, what we call the period of rotation, and period we abbreviate with a capital T because, with a capital T because it is an amount of time. All right, period is by definition the amount of time for something to go through one full circular something, rotation or revolution or cycle or whatever you want. All right, measured in seconds. It's an amount of time. A car takes 41 seconds to go around a circular track. Sure. Oh yeah, an amount of time to go around once. Time for, time per event. All right. The other one's called frequency. We abbreviate lowercase f, and that's a number of things that happen per unit time, per second. Notice, this is events per second as opposed to seconds per event, right? Seconds per event here, events per second here. Now, this gives us a new unit, right? The per second, or hertz. You also see it like this, per second. It's called a hertz, which we abbreviate capital HZ, right? So here, notice, a vinyl LP spins 33 times per minute, right? This is a number of events per unit time. If we did this, 33 revolutions, well, revolutions isn't so much a unit, right? We can just say it's 33 per minute. Well, that would be, in a minute, there are 60 seconds. So this is, let's call it 0.45 hertz. Because we're left with, notice, per seconds. Okay? So, while it shouldn't be tricky, it can be. I understand it definitely can be. Real big deal. Can you discern between a period and a frequency? All right, they'll show up in a bunch of questions. Oh yeah, like this one. Each rotation of a dentist's drill takes that many seconds. What's the frequency? Well, notice. Let me do this. notice that this is an amount of time. And notice it's each rotation, one rotation. So that is a period. Okay, we have a period of 2.5 times 10 to the negative fourth seconds. And the question is, what's frequency? Well, if we look here, this shows us, or if we look, here at the units, it ideally leads us to a pretty simple relationship between period and frequency. All right, if periods measured in seconds and frequencies measured in the inverse of that, well, what that says is that period is equal to 1 over frequency, or that frequency is equal to 1 over period. They are just inverses of each other. All right, so the frequency of this dentist drill is 1 over 2.5 times 10 to the negative fourth seconds. Or that's something like 40,400, I don't know, hang on, 2.5 e negative 4, and then that inverse button, love that inverse button. Yeah, 4,000 plates. Okay? So, as simple as those get. A little more complicated, probably. Oh, yeah, okay. Now, when we talk about velocity, it's really an instantaneous velocity. So I don't know why I write average here. Well, because it's hard to calculate instantaneous velocity when things change direction. But what we can do is say if something goes around in a circle, what's its average? I mean, this is good. Really, what's its average speed? Well, if we say that speed here, really just calling this speed is distance over time. Well, the distance that something travels in a circle, a special distance we know, is circumference. And the time it takes to go around one full loop is what we call the period, right? So that means that we can write this speed, and there's lots of ways to say this, but VT, this means what I call tangential, because the velocity, I should go back. The velocity, the instantaneous velocity, let me go back here, maybe back again to here. Yeah, at any instant, right, what we should make sure that we talk about is, here is a centripetal force, right, or acceleration. Those both point in towards the center. But if this thing, let's say, is going around in that direction, at this instant, the object is actually moving in this direction. All right? It's moving at any instant tangent to the curve. Hence that T for tangential. Right? Here it's moving in that direction. VT. Big deal. All right? At any instant. That's the direction the object is actually moving. Right? If this, again, top view, right? If the force that was making this thing accelerate towards the center, right here, if that force, instantaneously stopped or just went away, the object would move in this direction. It would move tangent to where, tangent to its location on the circle. Big deal there. Oops. Good. All right, so if we want to find the magnitude of that velocity, or we want to find the speed, we do, does it pop up for me? Where are you at? Yep, there it is. 2 pi r, or pi d, for circumference over a period. All right, one big equation there. There's Earth's radius. How fast are people in Ecuador moving? Ecuador is on the equator, hence, maybe. Hey, what's up? Hang on. Okay, sorry. Yeah, so let's do a little top view. Do a little top view here. If we have, here's the North Pole. That's a pretty damn good circle. Sorry. Here's North Pole, let's say here. So here's a person at the equator. Hello, Ecuadorian. And this radius is, well, we'll call it RE. Right? How fast are people moving? Well, let's see. V is 2 pi r over t, or in this case, 2 pi radius of the Earth over, this t. time it takes to go around once. Oh yeah, we call that a day. Let's do it in meters per second. Well, let's see. That means in a day, there are 24 hours. And then in an hour, there are, check this out, an hour, 60 minutes, and then in a minute, 60 seconds. So we can go that in an hour, there are 60 times 60 seconds, or 3,600 seconds. So, let's see. Yeah, well, do the math, folks. So V is, let's see, 2 pi times 6.37 E6. What's up, Cam? Oh, you might notice I'm taking this into meters. Kilo means 10 to the third, so this is 6.37 times 10 to the 6th meters. Should look familiar from the homework. All right, so V, I get 463 meters per second. That is what we call their tangential velocity. You'll see that written, or you'll see that referred to as, you'll see it as speed, you'll see it as linear speed, you'll see it as plain old velocity, you'll see it as tangential velocity. So anything that refers to how fast, I mean, this is what they're talking about, all right? That's how you're going to do it, typically, okay? Fair enough? Now, I shouldn't say it's going to happen all the time, because there are a couple other relationships that have to do with speed that we're going to get to, right? And a big one is this centripetal. Well, how do we actually calculate the size of centripetal forces, or how do we relate them really to other quantities, or how do we relate the magnitude of acceleration to other quantities? Well, oh my, what happened? Yeah, well, here's how we can do it. Now, I don't even know if you have this slide. I might yank it. This derivation is not necessary for you to do, but again, I like to show that things aren't magic. All right, let's look at, again, a top view, let's say, of something moving in a circle. All right, there are among the infinite numbers of velocities that it has, 4 of them at these 4 instants. Okay, now if we want to do what the heck is this? Oh yeah, if we want to do delta V, right? If I want to do acceleration delta V over t, well, delta V from instant 2 to instant 1 is V2 minus V1, or V2 plus negative V1. So here's negative V1. All right, I get this vector. There's that delta V. Well, notice I get the same vector if I just put them tip to tip. I know we said never do that. But if you put them tip to tip and go like that, same vector, right? Same vector here and here. So that says, well, from 2 to 3, the change is like that. From 3 to 4, the change is like that. From 4 back to 1, the change is like that. And the total change, the magnitude of the total change, is literally the perimeter of that square, right? Find the lengths of those vectors. Well, the deal is there aren't just 4 velocities. There's really more like 8 velocities, right? There's really more like 16 velocities. There's really more like, I don't know, there's really an infinite number of velocities. Where if we want the acceleration, what we do is find the total change in velocity in one period, right? That's the total change in one period. Well, the total change is not the perimeter of this square, but the circumference of this circle. Where the circumference of the circle is 2 pi r, and the time it takes is t, except, here's the big deal. The radius of that is not the radius. So here's the radius of an actual circular path. Notice, these vectors are not radius of the circular path, they're velocities. We use velocity vectors, right? like we use v1, v2, v3, v4, we use those velocities, those velocity vectors, to make this circle. So r is really v, and v is really 2 pi r over t, which means that acceleration is, I don't know why that pi is so small, 4 pi squared r over t squared. Oh gosh. Now if you notice, since we had v is 2 pi r over t, it looks like we just square everything to get this. Well, we square everything except for the r. So if I did v squared, that's 4 pi squared r squared over t, whoops, not subscript 2, t squared. But I don't want the r squared, so I do this. And oh yeah, there's centripetal acceleration. So two ways to write the magnitude of centripetal acceleration. 4 pi squared r over t squared, or v squared over r. All right, this is the one you absolutely need to have at your fingertips. Which means, very simply, that since net force is ma, then centripetal force is mv squared over r. And this one you absolutely have to have at your fingertips. Okay? Okay. Yeah, you've seen this kind of thing before in our gravitation little unit. All right, what happens to A if velocity is tripled? Well, notice, this is not a linear relationship. It is a quadratic relationship, right? We're going to get 9 times A, because whatever we do to V, we do that squared to A. What do we do to A if V is cut in half? Well, A would be cut in half squared, or cut in quarters. Right? Quadratic relationship between A and V. What happens to A if R is tripled? Well, there's an inverse relationship between A and R, but it's not the inverse square like in gravitation. So all we do is divide A by 3. Whatever you do to one, you do the opposite to the other. That's the nature of the inverse relationship. What do you do to A if R is cut in half? Well, whatever you do to R, you do the opposite to A. We get twice the acceleration. Okay? What do you do to F if V is doubled? Well, again, there's a quadratic relationship here. So that gives us V. Oh, yeah, you should do these. Oh, I love that word. What happens to F if V is thrice? I think I made that word up. Thrice, I mean divided by 3. That's what I mean, divided by 3. So, take a minute, maybe pause, see what you get. Here's what I get. Questions there? All right. Okay, a couple of questions. Oh, now these are, excuse me, like these, but where I change more than one thing. All right? Let's see. A certain force F is required to spin a ball in a circle at a constant speed. Now, let's see. We increase the ball's velocity by a factor of 4. Well, that would, how much force is required now? That would increase the force by a factor of 4 squared, or 16th. But here we also double the radius. Well, doubling the radius would give us half the force. So you combine these and we get a total force required now of 8F. And again, if you don't dig that, you can do this. F is mv squared over r. If you start the first one and say, okay, mass of 1, velocity of 1, radius of 1, oh wow, we get 1, right? If we, let's see, doesn't say anything about the mass, keep that the same. Quadruple the velocity and double the radius. Oh yeah, that's 8, right? 8 times as much. Right? So if you want to use those simple numbers, feel free. Car A. Car A drives around a curve of radius r at speed v. Frictional force F allows it to do that. Car B's tires can provide only half that force. At what maximum speed can car B travel around a curve of radius 2r? Oh boy. So at what speed? So I guess we can do this, right? F is mv squared over r. Let's express this in terms of v, or we'll solve it for v. F r over m square root. Well, it doesn't say that we change anything about the mass, but for car B, we can say that it's f over 2, and the radius is twice as much. Well, notice that's the same as this, f r over m. That's the same as a, right? Because this is our expression for a. Here's our expression for b. So yeah, same thing. Fair enough? All right. The classic car on a curve question. I almost hate to tell you how to do this already. I want you to try to struggle through it, so I'm going to make you do that. That'll be in your homework. Good. Now this one, we can go here. 50-kilogram child on the rim of a merry-go-round, radius 2 meters, not very big. Constant speed is 6 meters per second. What's the child's centripetal acceleration? Okay, this is more like it. This is pretty straightforward. We say that centripetal acceleration is v squared over r. Boom. 6 meters per second. Don't forget to square. 2 meters. That looks like 18 meters per second squared. Yikes. We call that pulling 2 G's almost. 1.8 G's. Because G is 10. Here's 18. That's 1.8 G's. What's the minimum force between feet and carousel required to make him do this? Well, you know, that frictional force, it's got to be a frictional force. That is the centripetal force in this case. So that's mv squared over r, or just ma. So 50 times 18, I believe, is 900 newtons. All right, so we have to notice this. We have to be able to recognize this. The question doesn't necessarily say, what's the centripetal force? It says, what force, you know, look at this, required to keep him in a circular path. Oh yeah, that's centripetal force. All right, it might say, what's the frictional force? And not even tell you, you know, required to keep him in a circular path. But if they're referring to the force responsible for allowing the object to move in a circle, they're telling you calculate centripetal force. What minimum coefficient of friction is required? Let's see. So that sounds like that's the only equation I know with with coefficient of friction. And here, you know, here's sort of our end-on view of the merry-go-round. Here's the kid. Forces we can draw. We can say this is mg. That's normal. And here's the frictional force. We get this view. It's not a top view. Top view would look like this. It's this donut where we take it and sort of flatten it out. Can't draw that, what I mean, but you know what I mean? So the view here would just, all we would see is this frictional force. We can't see the up and down, so we're sort of looking from this way. You get me? Well, that means that mu is that, which is, well, this, which is 500 newtons, right, mg. Wait a minute. We get m of mu of 1.8. Right? Yeah, 1.8. Oh, right. Is the answer you found reasonable? No. In other words, is he likely to stay on the merry-go-round? No. Child falls and hurts himself. Sorry, everyone. Yeah, not likely to stay on the merry-go-round. Okay. Okay. Now, this problem from the last page, you are equipped to solve. All right, I will say try it. You'll see the same problem or a very similar problem on the homework that I give you tomorrow when you come in. All right, but this one is you're equipped to solve. And I will say the free body diagram will get you there. The majority of you will get this. You're going to see something cool. Notice, I don't give you the mass of the car. What do you think that means? All right, don't let that stop you. Don't let that dissuade you from pressing forth with the physics. Okay? All right, folks, good start. A lot of info there. Sorry it's a long one. Just want to get the groundwork laid. See you tomorrow.